Alright, let's now take a look at the famous kernel trick. And I'll do it using an example. So we have two vectors here, x with components 1, 2, 3, and y with components 4, 5, 6. Yeah? And we're going to apply a transformation of these vectors, and the transformation will take all the dot products, all the combinations of the dot products of the component. So let me explain this a little bit. So we will apply here a phi of x, we can call this z, and we go from 3D to 9D. Yeah. How do I get to 9D? Well, we're gonna take the dot product, all the possible dot products of the components. So we have x1, 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 x2, x1, x3. Yeah. Then we have x2, x1, x2, x2, and x2, x3. And then we have x3, x1, x3, x2, and x3, x3. So that is my transformation. Yeah? And you see it's 9 dimensions. How we would typically do it is, well, we would calculate the phi of x. And that would be 1 times 1 is 1. Yeah? The next element would be 1 times 2 is 2. The next element, 1 times 3 is 3. And then we have 2 times 1 is 2. 2 times 2 is 4. And 2 times 3 is 6. And then we have 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. So we go from a 3-dimensional to 9-dimensional. Then we have phi of y is 4 squared is 16. 4 times 5 is 20. And 4 times 6 is 24. And now 5 times 4 is 20. 5 times 5 is 25. And 5 times 6 is 30. Then 6 times 4 is 24. 6 times 5 is 30. 6 times 6 is 36. So that is what my vector y will look at once we transform it to 9-dimensional space. So we could call this z1 and this z2. And remember, in our famous formula we have the dot product at the back, z transpose 1 times z2. Yeah. So this is a z transpose, z1 transpose is this one here. Yeah, is 1 times 9. And z2 is basically the column vector, is 9 rows, 1 column. So this is 1 times 1, exactly what we expect, and we expect the scalar. Okay, so let's calculate this dot product. So 1 times 16 is 16, plus 2 times 20 is 40, plus 3 times 24 is 72, plus 2 times 20 is 40, plus 4 times 25 is 100, plus 6 times 30 is 180, plus 3 times 24 is 72, plus 6 times 30 is 180, plus 9 times 36, that's 360, 330, 324. Yeah, and this is equal to 1024. Yeah, you can do the calculation, but that is what give you in terms of dot product. Okay, now what if we had a sort of kernel function between x and y, yeah, that would allow us to get that result much faster. And a kernel that we could envision is a kernel xy, and these symbols mean that it's a dot product, and then you square. So we have 1 times 4 is 4, plus 2 times 5 is 10, plus then 3 times 6 is 18, and we square this, and if you calculate this is also 1024. So this one here is much faster. Much faster, and you save all the work of making all these transformations. You don't care what phi is. Yeah? Phi can be anything. Just give me the beginning situation and give me the kernel, and I'll give you the outcome. Yeah? That is basically what a kernel function is. It allows you to work with your base factors in your original space and do calculations that would actually need to happen also in the high dimensional space. Yeah, so this is crazy. Yeah, this is fantastic. These kernels are not something very rare. Huh? There's several kernels that exist. We have the linear kernel, we have the polynomial kernel, and this is basically the kernel that we used in our example, to the power of p. So polynomial, in our case p was 2. Yeah? And then you have this kernel here, and this should make you think about one famous continuous distribution that we discussed in the past, and this is called the radial base function kernel. So it's radial base function. My advice is, for your coding exercises, just take this one. It works out of the box. Everything is linearly separable with this kernel. Yeah. So just how you did not see 1 plus, right? We said x1, right? But remember that in machine learning we have x0, w0 plus x1, w1, and so on. Remember that x0 we put equal to 1. So typically if you have two vectors, you have one here, and your other vector is here, and here you have 2 more and 2 more. It's this 1 times 1. This is basically this one here. Yeah? We didn't put 1, we just put a number in our example. But we use the polynomial, and you've seen it works pretty good. Yeah? And we can go to 100 million dimensions. So it's very easy to do. Okay, that was it for support vector machines and the kernels. Very powerful algorithm. We will try to apply it to all the coding exercises that we've seen. And we'll also take a new coding exercise into account. See you next time.